In this work, we introduce an optimal motion planning framework for quadruped jumping to generate versatile energy optimal quadrupedal jumping motions automatically. Quadrupedal animals are distinguished by their agile jumping movements. Jumping motion planning in challenging natural environments for quadruped robots is not effortless as imagined. A significant challenge is generating trajectories in feasible regions of different jumping tasks while satisfying the kino-dynamic constraints such as physics constraints, obstacles avoidance. Furthermore, the more complex facts are how to find the best trajectory in all those feasible regions. We propose a heuristics-based optimization jumping framework which can generate various jumping trajectories. But unlike most prior gradient-based trajectory optimization framework, no prior information is required in our framework such as contact schedule and an initial motion plan. Based on a general assumption of single rigid body and there is no compound rotation of body, an oblique symmetrical planar model with two legs is captured to describe the jumping motion in our framework. Meanwhile, for our framework, we categorize the jump motion into 4 phases according to the contact between the feet and the ground, which is 4 feet contact, 2 feet contact, flight and landing. Jumping motions of the quadruped robot can be realized by planning the contact force of each feet. The contact force of different jumping phase can be expressed in a polynomial equation with respect to time. However, the range of the contact force coefficients are not clear, which makes the optimization problem difficult to solve. So by substituting contact force into simplified centroidal dynamics and integrating, we can obtain jumping motion states of each jumping phase with respect to contact force coefficients, jumping phases duration and initial states. Thus, contact force coefficients can be converted into parameters with physical meaning. Considering the hardware and environment limitations of the robot, we introduced the following constraints in our jumping optimization framework, which include contact force, friction cone, joint angle, joint velocity, joint torque, joint position and obstacle avoidance. To deal with all these constraints and obtain energy-optimized trajectories, we propose a priority hierarchy fitness function. The convergence speed of the optimization algorithm can be accelerated by giving different priorities to different constraints. After we obtain the optimization variables, fitness function and constraints, the jumping problem can be transformed into an optimization problem. Because of the power and efficiency of the differential evolution algorithm for solving optimization problems over continuous space, we have chosen the differential evolution algorithm for our framework. From different jumping tasks optimization, we can see that the fitness values seem to influence by jumping complexity and the area with feasible region with obstacles. The lowest convergence shows by side flip. To address the differential evolution algorithm time-consuming problem, we proposed an offline trajectory library. The fundamental concept here is random obstacle information in aerial and ground situations, with jumping without barriers being a different circumstance from jumping with existent obstacles. Furthermore, the entire trajectory is sorted with energy value from minimal to maximum and then saved in a YAML file as key and value pairs with the trajectory name for trajectory selector. When the high-level information is submitted to the library selector, the selector based on Euclidean distance between the high-level information and the points in the pre-motion library will choose the best trajectory filename and load it into memory, which is speedy, taking about 0.26 milliseconds to load the file for the robot to execute the trajectory. The proposed framework has been successfully validated only with a simple continuously tracking PD controller in an open-source mini cheetah by several challenging jumping motions. We designed our experiments in 3 categories: normal jumping motions, flipping motions, and jumping with obstacles. The normal jumping motions have 5 types: front, rear, left, right, and a yaw spin jump. The flipping motions have two types: back and left flip. The jumping with obstacles motions have three types: front jumping through window shape obstacle, front jumping to desk, and left flipping through obstacle. Our primary contribution are summarized as follows. First, a new optimal motion planning framework based on meta-heuristic algorithm has been proposed for quadruped jumping, which does not require prior information. Then, a prioritization fitness function via kino-dynamic constraints is first proposed to deal with numerous nonlinear constraints of the optimization problem to produce trajectories in this jumping framework. Next, a pre-motion library with finite solutions is established to circumvent the issue of lengthy optimization durations. Finally, the proposed framework has been successfully verified with a variety of jumping motions on a real quadruped robot using just a simple joint-level PD tracking controller. Our future work can be shown as follows. First, the landing accuracy of jumping in our optimal framework has not been considered in this version. Then, a new flight phase controller should be added in our framework. Furthermore, the landing phase controller with different ground environments also should be improved to enhance the robustness of our framework. Okay, that's all. Thank you everyone.